Okay, so continuing our look, we have another two-part problem. A 12-volt automotive battery or automobile battery is connected to an electric starter motor. The current through the motor is 233 amp. How much power does the motor dissipate? Which is kind of weird terminology. Basically, how much power are we giving to the motor that it is then using to do its job? To put this in perspective, this is an electric starter motor. When you get in a car and you turn it on, you turn the key and you hear that weird noise, and then all of a sudden does that for a short time, and then the car starts going, and you hear the engine going, and it goes to the regular stuff. That's the starter. And what you're doing is the battery is supplying a lot of electrical power to that, and the starter is actually kind of pushing the engine to get it going, including doing things like firing the spark plugs, possibly a couple of other things. And if you think back once again to when we covered thermodynamics in class, we actually looked at an engine, and we talked about this, where the pistons would come up, you'd have a spark plug fire, and that could actually burn some of the gas and drive the piston down to actually get the car going. When you go out to the car, the starter is a small motor, basically, that's set up to get the whole engine up and running, hence why it's called a starter. Now, it takes a large amount of power, and it gets it from the battery to get the whole thing started. And that's why if you have a dead battery, you go out to your car, you turn the key, and nothing happens, because it needs to get its energy from the battery. And if your battery is getting kind of low, where it's not supplying enough energy, sometimes you'll hear the car try and turn on, you hear that starter going, but it never actually gets the engine going because it doesn't have enough power, it doesn't have enough energy. Two different things, but power is how quickly you're getting. All right, now that we've talked about that, let's look at our automotive battery. We, once again, not that it's terribly important, have a positive terminal and a negative terminal. And we have a delta V across them, a potential difference, aka a voltage, of 12 volts. I mentioned before that this is a pretty standard value for regular car batteries. It's connected to an electric starter motor. The current through the motor is 233 amps. So when you turn that key initially, I don't know, I could be wrong, it might actually get up to 233 amp, though I doubt it. But it is going to put a couple of amp through that starter motor. It's going to be a lot of power initially. I should double check and see exactly how realistic these values are, but whether or not they're realistic, they're the numbers that we're actually using for this particular homework. These are my numbers, yours might be a little bit different. They're asking how much power the motor dissipates. In other words, what we're saying is, how much energy are we giving to the motor? And then that motor is taking that energy and putting it somewhere else. In this case, getting the engine started. That's where pretty much most of this power is intended to go. So what they're actually asking is, what's the power that we are supplying to the motor? Well, power is going to be equal to our current times our potential difference. All right, so our power is actually going to be 233 amp times 12 volts. Power. 233 times 12 volts gives me 2,796. The power output of this probably entirely too much, though I could be wrong, that's not an incredibly bad value. 2,796 watts. We put SI in, amp and volt, we get SI out. The SI unit for power is watts. About 2,800. To put things in perspective, a strong microwave, when you actually turn on a microwave oven, a lot of times I think the one that I have at home has between 1,000 and 1,500 watts. So in other words, this isn't an outlandish number, although I think it's a little high for the car battery, though I could be wrong. This might actually be a pretty realistic value. I'm not an automotive engineer or a technician, and therefore I haven't actually looked at the currents themselves. If I get some time, I may go take a look at it. Or you're welcome to as well. I'd love to hear back if this is actually realistic. All right, this is part one. Part two is how much energy, so now they're asking for the energy, does the battery deliver to the motor during a 5-second period? The time that we're looking at is 5 seconds. Well, here's one of the equations that we've talked about before. Power is equal to energy divided by time. and multiplying both sides by time, we can find that the energy will be equal to power times time. We just found out that we had 2,796, was it? 96 it is. 96 watts, there's my power, and my time is 5 seconds. All right, so my energy will be 2,796 times 5. We end up with this times 5. We end up with 13,980 watts times seconds. Here's why, in case you kept wondering why I kept asking you what units are made out of, a watt is actually a joule per second. It's energy divided by time. Times seconds, the seconds cancel out, and I am left with joules, the SI unit. This is just shy of 14,000 joules. That's a decent amount of energy. 13,980 joules is the correct answer. So that's how we go about solving that. You'll see that this is very similar to some of the previous ones that we actually had on the homework as well.